So we have the mass, right? This is actually subjected to an excitation force of 200 cos 10 t, right? The value for the spin constant that is given as 4000 newtons per meter, and the damping coefficient is given as 14 newton seconds per meter, mass given, and these conditions are very important, right? We call it initial conditions, right? So initial conditions are also given, right? So what are those? X of 0. Now we know that this x is actually, it is a function of time, right? So the displacement when time is 0 seconds, that is 0.1 meters, right? And x dot, which is the velocity, right? The velocity when time is 0, that is 0 meters per second, right? Now we already know, we have an idea about the solution. We know that if I am going to consider the total response, it is actually the summation of the transient response and the steady state response, right? So this is the solution that actually comes under the transient response, right? And this is a very special term, which is omega d, which is the damped frequency, right? This special equation comes, right? You know that this special equation comes when beta is lesser than 1, right? Which is actually called the underdamped situation, right? So now let's proceed with the calculations, right? First of all, let's write the equation of motion, right? So I'm going to apply, I'll better write it here, mx double dot acting downwards, right? Because that direction I'm going to consider as the positive direction, right? And this excitation force is also acting along the same direction. So what is that? 200 cos 20. So now we have previously studied, right, how we can obtain the total response, right? And we know that the total response is actually a summation of the transient response and the steady state response, right? And we know the equation, right? And here this omega dt, right? Specifically this omega d, which is the damped frequency. So that's a very important part that specifically comes when you are going to consider that beta, which is the damping ratio when beta is lesser than 1, right? So if you are going to consider that special case when beta is lesser than 1, then we have to introduce this omega d, right? So here we have the excitation force 200 cos 10 t, right? So this is the excitation force that is actually according to the format of p cos omega t, where this omega is the angular velocity of this excitation force, right? So now we actually know what is our response, right? Just for your knowledge, right? If you want to write the equation of motion, right, so we can simply write it in this format. We already know that, which is mx double dot, that is actually acting downwards, that equals, right? Because if I am going to consider x along the downward direction, that displacement along the downward direction, right? If I say mx double dot, that equals, so what is the force that is acting in the similar direction as of the mx double dot, because we consider the displacement x is towards the downward direction. So that direction we are going to consider the positive direction, right? So this excitation force is going to that same direction, right? So that equals, we can say, just for the knowledge, right, let's consider this 200 cos 10 t based on this as according to this general format, right? Let's call it p cos omega t, right? So we can say that it equals p cos omega t, right, minus, now we already know that, in case if you need that you can refer to the previous recording, right, that equals the reaction that is exerted on this mass, so that is given by minus kx, and the reaction force that is exerted on this mass by the damper, which is Cx dot, right? We know that, right? So now we can obtain this nice equation, which is mx double dot plus kx plus cx dot equals p cos omega t, right? So this is how we can obtain this equation of motion, right, for this particular system, right? So now we don't have to worry about that, because now we have already derived how we can actually obtain the total response, right, which is the transient response plus the steady state response, right? So let's consider one at a time, right? So let's consider the transient response, right? Let's consider the transient response. We know that is e to the power minus beta omega n times t within brackets a cos omega dt, right? Better put this kind of brackets, right, because this is a cosine of a certain angle, right, plus b sine, again put brackets omega dt, right? What is this? This is the transient response, right? So let's keep it there, right? Now we have to calculate what is beta, what is omega n. Now t is actually, that is the t represents time, alright? So this a is a constant that we have to determine, and this b is also a constant that we have to determine, alright? Now let's focus the given data here, right? So we know that 2 beta omega n, alright, that equals the damping coefficient divided by the mass, right? 2 beta omega n equals c divided by m, right, from the fundamentals, right? So then beta equals what? Beta equals c divided by 2 m omega n, right? So that's a one part, right? And also we know that the natural frequency omega n, that equals root k divided by m. We know what is k. K is the spin constant, which is 4000 newtons per meter. So k is 4000, right? What is the mass? Mass is given as 10 kilograms, right? Just divided by 10. You can cancel, you are getting 400. What is square root of 400? That is 20 radians per second, right? So I will delete this now. So I will write the value here, 20 radians per second, right? And from that we can calculate what is beta. C is 40 Newton seconds per meter. 40 Newton seconds per meter. C is 40 divided by 2 times m is 10. This is 20. Alright. So that equals 40 divided by 2 into 20, 40 and 400. So 4 divided by 40. What is that? 1 over 10, that means 0.1. So what is our beta? Our beta is 0.1, right? Within brackets you can write underdamped. Alright. So now we have an idea about the fundamental values that we should know, right? So then we have to find the damped frequency, right? So how can we find that? So now I'll better erase these things, right? Because I need this space, right? Now we know the damped frequency omega d equals omega n times 1 minus beta squared. Alright, so omega n is 20, 1 minus 0.1 whole thing squared, right? So if you carefully do the calculations, right, so this value you will obtain as 19.9 radians per second. Be very careful, it is, don't say that it is 20, don't get the wrong rounded value, right? because if you do this simplification, that is so clear that it is not 20 radians, that is definitely lesser than that, right? So if you do the calculation, that is omega d, that damped frequency value, or that damped angular velocity, so that is 19.9 radians per second. Alright, so that part is also clear. Alright, so now what we can do? So now we can further simplify this, that equals e to the power minus beta times omega n. What is omega n? Omega n we know that is 20. What is beta? 0.1. So 0.1 into 20, how much? That will be 2, right? So minus here, beta is 0.1 and omega n is 20, and t, that is the variable. So this will be minus 2 times t. Alright? E to the power minus 2 times t, right? Put some brackets, right? A cosine 19.9t, right? Plus b sine 19.9 t, right? Right. So this is the transient. So this is our transient solution. Alright. So now let's focus the steady state response, right? Which is the other part, right? Steady state response, which is actually based on the particular integral, right? So now x steady state, right? Now steady state response, right? We know that there is a mechanism behind that, right? Based on the fundamentals and based on the basic derivations, right? We say that let the steady state response to be delta, which is the static deflection, right? And neta, which is the dynamic magnification, times cos within brackets omega t minus phi, right? So what is this phi? This phi is actually the phase angle, right? This phi is actually the phase angle, right? And why it is minus phi? Because we say that the total response lags by 5 radians, right? Or in case if you want, you can consider that in degrees, right? So we say that practically the total response lags by 5 radians with respect to the excitation force. Alright? And I hope that is clear, right? So now here, now we are actually okay with this delta, which is the static deflection, right? That is given by that particular magnitude of the force divided by that overall spin constant, that k value, right? But our problem is, so what is this neta here? So let's consider what is this neta now, right? So now we have already obtained this part, right, which is alright. So I will write it here. Focus this one, right? So now we all are okay with this delta, right? But we have derived this equation up to this omega n whole thing squared, right? And that is divided by omega n squared minus omega squared whole thing squared, omega n squared, omega squared whole thing squared, right? Plus 2 beta omega omega n whole thing squared, right? So we have, I'm only going to consider this part. All right. So now here, right, I just want to teach you something, right? So here there is another very little simplification. All right. Here you can observe this omega n squared, right? So that part, will better send that part to the denominator in this way, right? We know that here it is omega n squared divided by this part, right? So we can shift this omega n squared under, or we can shift this omega n squared to this denominator in this moment. Is that clear? Right. So we can, let's keep 1 there, right? And I hope that is clear, right? Previously that omega n squared was here at the numerator, right? So we can write the same thing if you write 1 over 1 divided by omega n squared at the denominator, right? Because there is a simplification actually. Alright? So now as you people are okay with 5, I'll better erase this, right? Now just consider this part, right? Because now I want to teach you how did I obtain this neta, which is the dynamic magnification. This is the thing, right? Let's consider this part. So now we have 1 over omega n whole thing squared here. Exactly? And we have square root omega n squared minus omega squared whole thing squared plus 2 beta omega n whole thing squared. Right? So now this 1 over omega squared, right? We can include inside this square root symbol, right? If we include that in this format, omega n to the power 4, right? Because it's 1 over omega n squared, we can include this inside the square root symbol, right? So this omega n squared, that will become omega n to the power 4, right? Because if we take the square root of omega n to the power 4, that will give omega n squared, right? So I hope that part is clear. Alright? So now here again, right? This omega n to the power 4, we can further, because these steps are very important when it comes to the simplification, right? Alright, omega n squared minus omega squared whole squared divided by omega n to the power 4 plus we can separate this, right? 2 beta omega n whole squared. Alright, and also we know that frequency ratio, right? Frequency ratio R, right? Or that the ratio of the angular velocity of the excitation force, right, divided by the natural frequency, right? R equals this omega divided by omega n, right? Which is the equation for the frequency ratio, right? So now if you do this simplification, right, this simplification process, it still continues, right? Focus this part, right? So I'll go one by one, right? So I will consider this part separately and this part separately, right? So that will be easy for you to understand, right? Omega n squared, right? So this is what we have, right? Omega n whole squared minus omega squared divided by omega n to the power 4, right? So this one I can write alright, because I'm going to break this into omega n squared times omega n squared, right? Now this part will become what? 1 minus omega divided by omega n whole thing squared. Is that clear, right? Because omega n squared divided by omega n squared, that is 1, right? So 1 minus omega divided by omega n whole thing squared, right? Because the reason why I perform this, because I want to include this relationship into there, because we know that omega divided by omega, that is the frequency ratio R. Alright, so then this part will become, see, 1 minus R squared, right? because omega divided by omega n is r, right? So this part will get simplified, right? Is that clear? So I will just erase this. You can say this is what? 1 minus r squared. Is that clear? So this part will become what? 1 minus r squared, right? And I hope that part is clear. So we can further say 1 minus r squared, because we had 1 minus r squared times another 1 minus r squared. So we can say 1 minus r squared squared. I hope that is clear. If it is not clear, you can again refer to that, right? So this part now we have simplified, alright? Now the other part. So now I will erase this part because I need some space, right? So what is that? 2 beta omega omega n whole thing squared divided by omega n to the power 4, right? 2 beta whole thing squared omega squared omega n squared divided by omega n to the power 4, right? This omega n squared to this omega to the power 4 we can cancel, and we have omega n to the power 2 balance, right? So from here also we can obtain, see this 2 beta whole thing squared times, see omega divided by omega n, right? Omega divided by omega n but whole thing squared, right? Is that clear, right? So what is omega divided by omega n? So this also we can replace by r. So 2 beta, because this omega divided by omega n is r, so we can say 2 beta r whole thing squared. That looks easy, right? I hope that is clear. Alright, so then this part also we have simplified, alright, and I hope that is clear. So then we can obtain a simplified version, right? What is the simplified version that we could obtain, right? 1 divided by, put this square root symbol, 1 minus r squared whole thing squared plus, you can say 2 beta r whole thing squared. This is what we actually define as dynamic magnification, which is theta, right? Because what we had previously was this omega n whole thing squared divided by square root omega n whole thing squared minus omega squared whole thing squared plus 2 beta omega n whole thing squared, right? Because actually this part we had the ability to further simplify this part up to here, right? But we are not going to call this part as the dynamic magnification, but we define dynamic magnification as this, right? That is just for the purpose of simplification, right? Because simplification means, because we need to keep, every time we need to keep the most simplified version, right? So what's the next thing is, now we have to find the phase angle, right? So what is phase angle alpha? So that is, phase angle alpha is given by tan inverse, alright, 2 beta omega omega n divided by omega n whole thing squared minus omega squared, right? So now we have to find that, right? So that will be tan inverse twice beta is 0.1, omega is 10, natural frequency is 20, natural frequency squared, 20 squared is 400, omega is 10, so omega squared is 100, right? So tan inverse 2 into 0.1 into 10, 0.1 into 10 will be 1, 2, this will be 40 divided by 400 minus 100 means 300. So tan inverse 40 divided by 300, right? So $7.594, right? So I'll better say 7.59, but be very careful. This 7.59, that is in degrees, right? 7.59, that is in degrees, right? So I need to keep this value, which I need to keep this value in radians, right? So the radian value will be 0.1325 radians, right? So now we are okay with the 5 angle. What is the 5 angle? 0.1325 radians, right? Oh, let's write the other value as a reference, 7.59 in degrees, right? So be very careful to select the most appropriate that unit in your calculator, right? So that part is also clear, right? Now then we'll again focus this steady state response, right? Now what is static deflection? So what is the magnitude of this excitation force? That is 200, right? What is the spring constant value? 4000. What is neta? 1 divided by 1 minus r squared whole thing squared plus 2 beta r whole thing squared, right? So what is our r? This is the frequency ratio. We know omega is 10, omega n is 20, so frequency ratio is 0.5. All right, so then this cosine, what is omega t, right? Omega t we know, so that because of omega, because if I want to consider our excitation force, right, so our omega is 10, right, this part, right? So this will be cosine 10t, right? Don't forget to put the bracket separately to the cosine angle, right? So 10t minus 5. 10t minus 5, what is the value? 0.1325. 0.1325. Alright. So now let's write these values again. So if I keep all the values, that is easy for you to understand, right? So 200 divided by 4000, right? 1 over square root symbol. 1 minus, what is frequency ratio? 0.5 whole thing squared and whole thing squared plus 2 times beta is 0.1 and r is 0.5 and that one whole thing squared, right? Times cosine 10t minus 0.1325, right? So if you carefully do the simplifications, right? So let's do the simplification for that. After simplification, I am the simplified value for this part, right? I am obtaining it as 0.0, check the value, 0.06608, again 0.06608. It's better to call it 0.066, right? Or if you want, you can even call it 0.0661, but doesn't matter. Let's consider this value, right? 0.066, right? So that is better, right? Now I will further simplify the steady state response, all right? We already know what is the steady state response, right? How we have defined the static deflection delta and how we have defined the dynamic magnification, right? And how we have considered this part, which is based on the excitation force, right? So I'll erase this. So what is the simplified version of the steady state response now? So I will say X steady state response I will represent by SS, steady state, right? That equals 0.066, 0.066, right? Times cosine 10t minus 0.1325, right? So this is the part for the steady state response. But no, keep in mind, this is a very common mistake that most of the students are doing, right? Because when students are actually given the initial conditions, what most of the students are doing in the examination is that they are going to consider this. I mean, like, they first obtain the transient solution, right? They first obtain the transient response and they are going to apply the initial conditions to the transient solution. No, these initial conditions these initial conditions are actually given for the total response, right? Not only for the transient part, not only for the part answers, right? Because initial conditions are given for the total response, right? I hope that part is clear, right? So don't apply these initial conditions only to the transient solution, so that you can comfortably find this value, right? So now we'll complete this part with the total response. Let's say x total, right? I can say x total response. So that equals what? The transient response, right, plus x steady state. Alright, so this part we know. Now we have simplified e to the power minus 2t times, but still we have to determine what is a and b, right? But before determining that, we have to obtain the total response, right? E to the minus 20 times a cosine, put brackets, 19.90 plus b sine 19.90. All right, close this one, right? All right, plus 0.066, right? Cos 10t minus this one, cos 10t minus 0.1325, right? Because doesn't matter, I will again write that. So x total, so what is x total? E to the power minus 2t times a cos 19.9t plus b sine 19.9t, close that, plus 0.066 cosine, put brackets, 10t minus 0.1325. I hope now that is clear, right? Because I wanted to obtain that in a one single line. So this part is very important. So if you do not have an idea about how you should obtain this part, so then it will be difficult for you to proceed with the answer, right? All right.